Hello, everyone. Today we'll continue our intelligent exploration lecture due from last week. Because we lost our previous Wednesday's lecture, the idea is to replace it this coming Wednesday. Usually, I don't think we have school on Wednesday, right? We don't have school, but there will be a Zoom-only lecture that you can attend on the same time of your regular time. And will also be, the video will be posted. So if you cannot attend, but it will be still in your scheduled time. So most people will be available. So just Zoom only. This coming Wednesday is going to be Zoom only. Okay. All right. So these are the last lectures, but at the same time, they're the most exciting is where we see papers. I have at least lined up some amazing papers. One amazing paper we'll see today. On Wednesday, we'll also see some pretty wonderful things about sim-to-real transfer. And I'll show you some examples of reinforcement learning in simulation that has worked on real robots. You train in simulation and you generalize in the real world. All right. So we'll try our best. So for today, the idea is to learn. We'll do offline reinforcement learning by observation, but we still have one more important work to cover from our intelligent exploration lecture, okay? Now, the two topics are related, and you'll see how. So just to remind you, where we left last time was on how do we intelligently explore the world. We mentioned the importance of learning a model of the environment, and that model of the environment will inform us of things that we know and things that we do not know. We captured this notion of knowing the environment in terms of a parametric model that given a state and action predicts next state. And we added exploration bonus based on the error of that state transition function, okay? And then we moved on and we said, what if we don't use a parametric model to capture state transitions in the environment? What if we use a non-parametric structure to capture that? And we saw that paper, Exploration by Reachability, okay, where it was using an external memory comprised of nodes and edges. Nodes were states that you've been. Edges would reflect the closeness between two visited states. Each time you'd see an observation, you would compare that observation with observations in memory, okay? And if the distance is large, as given by a comparator network that we were training, if you remember, all these are trained jointly. If the distance is large, then you add it in your memory, okay? And you also, reward yourself. And if the distance is small, you say, okay, I've seen this before. I don't reward myself. I do not update my memory. One important thing that we said about such a non-parametric memory structure is its ability to learn fast. Each time you see a new observation, each time you see a new transition, you add it in your non-parametric structure and you know it. Why? Because the next observation will be compared against this expanded memory. While we said that if you have parametric functions, for them to learn a new piece of information require multiple updates of gradient descent, okay? Now, despite the fact that we're building this awesome, let's say, awesome in some way, let's say model of the environment in terms of a graph, our learning method is still kind of naive, right? A model-free reinforcement learning method, okay? Like PPO, if you remember, with just an additional exploration bonus. So clearly, a model is not just useful to evaluate your exploration. Clearly, it should add to your ability to learn your policy faster in more direct ways. And we will be visiting this type of methods from here till the end of the course, okay? So the next paper is called Go Explore. It is similar to our previous paper in the sense, again, we're going to have a non-parametric structure, which we're going to be expanding in terms of trajectories of states. So trajectories of states is still nodes linked with edges, where the edge essentially will denote transition from one state to the next. And you see how we'll use this extra parametric structure directly to learn a policy for the game. And we'll be able to do much better than a model-free method, okay? So we still are waiting for some revolution to come from such a non-parametric representation of the model of the environment, which the previous paper didn't show, okay? I mean, it says, oh, look, we're doing better than previous people because we capture an uncertainty better and our, curiosity better, great. But unfortunately, because they were using this PPO, let's say, and, model-free RL has limitations which could visit very explicitly in about 5 slides from now. They couldn't, let's say, bring some dramatic improvement on what the agent could learn, okay? Now here, this paper is very interesting. I really expect that you're going to read the paper carefully. There's not going to be any neural network in the first phase of the algorithm. Okay, the first phase of the algorithm is all going to be to expanding this memory structure of states, state transitions, and inferring, links, additional links that are missing between states. Okay, does this make sense? Okay, so now we'll see exactly what we mean by that. Okay, so if you remember last time, we said curiosity and curiosity-driven exploration and intrinsic motivation are very, very interesting formulations, right? Very, very biologically plausible. But why they have not showed so far, the way we incorporate in the algorithms, why there hasn't been a revolution? And they said here about the problem of detachment that the present methods use. So, not sure where I touched. Here, this guy. So what is detachment? Detachment is, I'm curious about this part. I'm going to start exploring it. I start from the beginning because I just died and I want to reset. And guess what? Now I'm not curious enough to go to the left. And because I'm not curious enough to go to the left, I also leave this part of the state space unexplored. Do you see? It's as if you have a long corridor of the museum with wonderful rooms, and the awesomest rooms are at the end of the hallway, but then you don't get to go to those great rooms because the rooms that come immediate, you are not rewarded, and your policy gets low rewards by visiting things that you've seen before. Is this how you explore a museum? No, you just have explicit map. By map, we don't mean metric map. We don't mean that you know how many meters is the door of one room from the other, but a landmark topological map of where you've been, what you saw there waiting for you, and so on. And you know how to direct yourself to that particular point where you left off and keep exploring and getting to cover everything that the museum has to offer, correct? Okay, so this is what these people are arguing about. They're arguing about exploring the environment in a much more systematic way, correct? Okay, so let's see how to do that. And by the way, if you remember, we said that I'll start exploring this way to the right. Then because I'm exploring to the right, I start forgetting about the left, okay? Unfortunately, because there's always interference when we learn in a parametric function, the new latest data interfere with the earlier data, right? This is the forgetting problem. Because all the weights are updated, if you keep replaying from latest data, you forget the old data, so then you start forgetting the nice first rooms that you saw. So then again, you start exploring to the left, and then the whole thing repeats. Do you remember the problem of detachment? Do you have any questions here? Do you want to repeat anything on? Okay, so the problem of not being able to learn fast and the problem of catastrophic forgetting of parametric neural networks is well documented in the literature and is also very intuitive, right? And I expect that you are familiar with it, okay? Okay, and then here it says that replay buffers do not actually remember because replay buffers needs to be very large, and replay buffers hold a lot of useless experience along with the useful experience and so on. And here what they're saying let's do what humans do. Let's just explicitly remember where we've been, which state transition to which, remember exactly where we left off, and being able to reset and start exploring from where we left off. Very simple idea, guys. Extremely intuitive idea. Now we're going to visit, okay? Now, imagine that you are going to the museum, as we said, and you've seen these 2 rooms, and then you go to the restroom, and then you want to go back to where you were. This assumes that you are able to go to that place, correct? So, I mean, if your policy cannot even get you there, then you have a problem. So these people solve this problem of getting back to where I was in a very direct way, which is state resetting. So I have a state, and I save that state, seeing, let's say, the entrance of the Egyptian room, okay? Then I save that state, and then if I want to go to that room, I just reset the simulator there, okay? Now they have a second paper, which they call First Return, Then Explore, where they learn a goal condition policy. The goal is the entrance of the Egyptian room, and I want to be learning policies to get me to states further and further away, and I don't need to reset the simulator. I can just, use my learned policy, correct? But in this paper, we will be using state resetting at training time. Many papers use state resetting at training time, just to be clear. Now, there's not going to be any state resetting at test time. Like when you're about to evaluate the agent you learned, there's not going to be any state resetting. Is that clear? Okay. And also, it needs to be clear why we're using state resetting, because we want to be explicit of where we left off and want to go back and keep exploring. Yeah, so what is the big idea here? The big idea is that we're going to have an archive, which is essentially a memory of trajectories, which is essentially nodes and edges. Nodes are the states, edges are the transitions from state to state, okay? And we will be updating this archive, we'll be updating this memory with new states that we reached and their corresponding trajectories. If we find shorter trajectories to get to specific states, that also will be adding. And also we'll be resetting ourselves to those states and continue exploring using our state connectivity map. So essentially just a memory of states and their interconnections. Okay, yes?
So then you have to keep a track between the length of each state.
They do keep track, yes. They just, yes, they have a humongous archive. All previous trajectories are there, okay? Now, one very plausible question, though, that you can ask is, how do they figure out when two states are the same or not? Because that's very important, right? I mean, for us, it's easy. For us, it's easy to know. I mean, when you play Montezuma's Revenge, you're like, oh, yeah, sure, here I am again. Do you see? So we're very good. It's like, okay, here's the monster, here's the cave, and so on. They also need to infer that. Now, of course, so by the way, this is applied to Montezuma's Revenge. And that state matching is a very important thing to recognize that, yes, I've been here before. And they solve it very easily because maybe in Montezuma's Revenge things work out. And I'll show you how. They just take the image and discretize it and make it much smaller. And this is the representation of a state. And then they compare when, two discrete versions of an image are the same. They say, yes, it's the same state or it's different states. Okay, very simple. So beyond detachment, so there's something else now beyond detachment. They have two main criticism. This paper has two main criticism against papers in the literature. The first was the detachment problem of the way curiosity-driven exploration was implemented in previous works. The second is the derailment problem that is common in every reinforcement learning method. So what is derailment? Derailment says the following. To be able to get rewarded in reinforcement learning, you really need to be very, very lucky to do things correctly after an insane amount of exploration. And let's say after exploring like crazy, you manage to go upstairs and get rewarded, okay? You're like, yes, I did it, all right? Now, what do you do with that awesome sequence of actions? You chop it and you throw it into the replay buffer along with tons of other super crappy transitions, okay? So these people say, this is not correct. You shouldn't do that. You should just save this. You should just save this. You should just save this good trajectory. You cannot just go in the trajectory and start adding noise. If you add noise, this good golden trajectory will probably lead you to something really crappy. Okay, so the way we explore is totally wrong. So these people are going to do more something like your colleague said last time. We're going to be using the model that we're building to also be learning a better policy. Okay, learn better actions as well. So here is the general solution, guys. So this algorithm has two phases. The first phase says, I want to be able to solve Montezuma's Revenge from the beginning till the end. I'm going to do that in a non-randomized simulator. I will, pick a random seed and the monsters will always show up in the same way. And so I'm not going to need to solve a very difficult representation learning problem, because the monster will always be exactly the same, and the door will shine exactly the same, and so on. So I will be living in a deterministic environment, in a non-stochastic environment, and I'll solve first the game from the beginning till the end. What does it mean to solve? I'll find a very, very long trajectory of states and actions that take me all the way from the beginning to the end, and I can do that. This is a deterministic environment. I will be able to be dying and then be going back to my trajectory by resetting and keep trying, and then dying and keep trying, and so on. Is that clear? Okay, so first I'll come up with this very long trajectory that takes me from the beginning to the end. And then, using the guidance from my golden trajectory, I will switch on stochasticity of the environment, and I will use this trajectory as my guidance, okay, to learn a robust policy. And this second part, I'll show you exactly details of how to do both. So you don't need to worry. We'll go into details in both. But that second part will be using neural nets, and we'll be using GPUs, and so on and so forth. And the first part will not use any of those. Okay, the first part, it's all about graph expansion and graph rearrangements, and add the extra trajectory, and so on and so forth. Check which trajectory that takes you from state 1 to state 2 is shorter, and keep this one and remove the other one, and so on. It's like a graph search, the first part. And the second part is robustification of the solution you found, and we'll give exact ideas of how to do both. And the first part is much faster than the second part. That's the interesting thing, okay? So now we'll go into details on this, okay? And here is now how this connects also to learning by observation. So why this way of casting RL in this way is related to learning by observation. When we learn by observation, we know what we expect to achieve. Somebody has showed us the trajectory. We don't need to discover how to open the door. We know exactly that somebody put his hand, turned the handle, and the door opened, okay? If we have basic perception system. Or let's say you go to a spaceship. You go to a spaceship, and you don't know how spaceships work, but then you see, the guide in front of you, and he press the right buttons. You just look at him or her, you look at them, and you repeat the same actions, okay? So you learn by observation. You don't need to do random exploration to discover the policy. And the second part is exactly this, the phase 2. The phase 2 has zero, it doesn't try to discover how the door is going to open. It's just trying to discover very tiny little policy adaptations to handle the stochasticity of the environment. Do you see? It's a much local problem, okay? So what I mean by that, but maybe the guide is much stronger than you, and he just did something like this and opened the door, and you did the same nothing moves. So you really need to use your both hands and put your arm and so on. So that's going to be the second part. You know the goal at every time step. You know what goal you need to hit, but you need to use your own actuation to get there. Does this make sense? Okay, so that's how learning by observation is also related here with this. Okay, phase 1. So here's what we're going to do. We're going to wake up in the first state of the game, all right? And we're going to do some insane random exploration. No curiosity, nothing here, okay? We're just going to do exploration. And we're going to remember which cells we visited. What are cells? Cells is just the picture, downscaled, all right? It's just picture downscaled. And each time at each, iteration, I need to decide where to wake up. We will be using state resetting. So which state is promising for me to wake up? Which state has unexplored states going forward, and so on. So this is similar to you going to a museum. You say, okay, yes, I've been in this room and I've explored all adjacent rooms. There is nothing for me to do in that room now, okay? I will wake up in a room where I remember that I left some unexplored. There were some doors that I actually didn't explore, okay? So you will wake up on states on the archive. So you'll go back there and you'll start exploring from there, okay? So you don't have the detachment anymore because you remember exactly where you left. So you will wake up there and start exploring. Okay, and as you explore, you also keep track. Do I see older cells or newer cells? Because if I see older cells, maybe, and the trajectories are also longer than I've been there before, discard that exploration, okay? And if I get some new cells, then I'll add them and their trajectories. So I build a big state connectivity map in this way. Each time I pick a state from the archive, go there, start exploring, add the new trajectories on my archive, and repeat. Do you see the iteration? Any questions on that iteration? Okay, so this is phase one, and this avoids detachment, as we said, okay, because it has a much more systematic way of exploring, and they don't use the example of a museum, they use the example of a house. You go at every little room. Now, this assumes, guys, just to be clear, this assumes you know, when you see a picture, you know in which cell you are. You know where you are in the map. And to be honest, this is an easy problem because this is a non-deterministic environment. So basically, even exact pixel matching will do kind of the job. You know what I mean? That's why this works here. Otherwise, you need very fancy representation learning to tell you, yeah, that stays the same. Sure, I mean, the scale, maybe the stairs is a little bit to the right, but still the same, okay? And so on and so forth. Just before you ask any questions, I just want to show you here the cell representation. So we want to be able to map, so this is the problem of representation learning. We want to be able to map similar states to similar cells, to similar nodes on our connectivity map, and semantically dissimilar states to different cells, clearly, okay? Now, these people didn't do any fancy thing for creating that, let's say you can think about the cell is essentially a non-learning way to talk about a feature representation of the state. So these people just, here, they did this one. They just downsample the image, and that's it. You just downsample. It's kind of dumb and fast, and it doesn't use any game-specific knowledge, but that's it. I'll show you how adding some domain knowledge information in a little bit, and this domain knowledge is in which room number you are, do you have a key or not? These two things. So knowing in which room number you are means that you will never make conflate two states where one is number 1 and the other is number 10. So this is very important information that imagine I give you as an oracle. I'm God and tell you, okay, this is museum room number 3. And then you're like, okay, yes, I'm sure. I know now that I didn't mix the two rooms, basically. That's the idea here, okay? So this will allow this algorithm to score much superhuman performance, that extra domain knowledge. So what is this domain knowledge, guys? This representation learning, this computer vision, to be able to see, yeah, I know this state. This state has the key. I know this state. I haven't seen the key yet, or I'm holding the key. These are the type of semantic information you need to be able to map an observation to the right state in your memory. Does this make sense? This is also very similar to what we did in our previous paper, where we would take two states and try to compare. Are they close or far? Okay, so does this make sense? So this is, again, we're trying to learn the right representation. Okay, so now that you know how they made cells, they say which cells I'm going to wake up. Well, I'm going to wake up to states that lead to new states and where I haven't woken up enough before. That's it. Okay. And is that clear? Now I selected the cell where I want to wake up. Now I actually need to get there. And these people are going to use state resetting, as we said. They say, oh, you can be learning goal condition policies. And the truth is that their goal condition paper was not as successful because actually that was a difficult thing to do. It is difficult to learn for every state of the game how to get there. This is the same reinforcement learning problem. Okay. And that's it. So you do state resetting. And you know how to reset because basically you know how to reset because it's a deterministic environment and you have saved the trajectory that leads you to that cell. So you may as well just do the same thing. Do you see what I'm saying? So they were criticized for switching off the stochasticity of the environment at training time. All right, this paper was criticized. But they said, it doesn't matter. We're just going to figure out what matters and what counts, what is important, what's not important for reinforcement learning. And we think that, we give big insights in this paper and so on. Okay. So there is absolutely no neural network here, guys. It's just not even to create the state representation. Okay. You just downsample and match the pixel values in that downsampled image. And you create a threshold and say, oh, below the threshold, it's the same cell. I'm going to go to the same place. Different threshold, different cells. Is that clear? Okay. The exploration is again extremely dumb. We're just going to be taking random actions, okay, for 100 time steps. And then the exploration stops. Then you look what cells you visited. If you visit new cells, you add them in your archive and so on. Is that clear? Is this process clear of phase one? All right. So now let's see how well it does. Well, it actually does very well. This is phase one. Is much, much, much higher than state of the art. And this is significant because you don't use any neural nets or this DeepRL mambo jumbo, you know what I mean? It just thinks about the model of the environment as a graph and tries to learn that graph. Okay? All right, not too bad. And let's go now to phase two. So let's repeat what we learned so far. So far, we described phase one, which is explore until you solve the game, simply by developing a state connectivity map and iterating between selecting a node from your connectivity map, waking up in that node, exploring for 100 time steps, adding the new states and their trajectories to the archive, if they lead to nodal states or to all states with shorter trajectories, and repeat. That's all we said. And now phase two is robustification. Yeah. So what is robustification? Robustification means that if your environment is not deterministic, so if your environment is deterministic, you're done, by the way. Okay? You have now your trajectory, you just replay it, and that's it. Now, the environment may not be deterministic, in which case you need to robustify your trajectory. How do we robustify? Now I'll go into details. Well, a robustification problem is essentially an imitation learning problem. But what imitation learning? Imitation learning from a single demonstration. And to be honest, this is the right setup for imitation learning. When you learn, do I need to show you 100,000 of times how to do something? You do it once, and that's it. I showed you once, and then you play a little bit with your own hands, and you do it, okay? So it's the same here. It's an imitation learning problem with a single demonstration, okay? So now we'll see how we can do imitation learning from a single demonstration. The phase one can be thought as a planner, guys. It's a planner. It makes it learns a model of the environment. And, we use this word learning by essentially means organizes the states, okay, and their trajectories. And now we'll use the solution from that planner to essentially learn a policy under stochasticity. So which method of imitation learning they decided to use? Well, there is this awesome paper, which we'll visit now in detail, which is called Learn Montezuma's Revenge from a Single Demonstration. Perfect fit, right? They also use a single demonstration, and they're in the Montezuma's Revenge environment, correct? So they'll use exactly that. So now I'll tell you exactly how. So here is the paper. Why we visit this paper? Because it has a very, very interesting insights. I really hope you read this paper, and the introduction is fantastic. The introduction, which actually will say the main message of the introduction. The main message of the introduction is that reinforcement learning is hopeless if the reward is far away, okay? And that's the first insight. The second insight is do not imitate actions. It's not useful to be imitating actions. You help yourself by resetting on the right state on the trajectory. Okay, it's all about the states on the trajectory. So I'll show you what I mean. And first you'll reset to the end of the demonstration, solve the problem. And because you reset it close to the end, it's a the reward is not far away anymore. Then you'll reset earlier in the demonstration. Again, you're going to solve the problem. Again, the reward is not distance because you know how to solve the remaining, and so on and so forth. And then you'll be resetting progressively earlier and earlier in time. Now you need to say, oh, but state resetting is cheating. Well, that paper's idea is that there's not actions that are important, are the states. Which states connect to what states? If you guys or the algorithm had an awesome representation to recognize states, it can use that state feature matching to track its progress throughout the demonstration. And it would not need the external reward of the environment. Do you see? You would be rewarded yourself saying, oh, yes, I reached the milestone. I was able to pick up the key. Then you see the demonstration that tells you go to the cave. You fall in the lava, you die. Try again and so on. You reach the cave. You're like, yes, I did it. There is no external reward in the environment. I don't care about the external reward because I have eyes and I can see that I'm tracking the demonstration. Do you see what I mean? So we'll see this. We're going to have one more lecture on learning by observation. And we will see this type of tracking of the imitator's trajectory. But okay, just to be, this is not here. This is still relying on the external reward. And that's why you need to do these crazy things of resetting towards the end. But I'm just trying to explain to you that if you have one demonstration, that's the natural way to learn to act, that you can see and track your progress and give rewards to yourself as opposed to relying on the external reward of the environment. Okay, so we'll see a paper like that. It's called Learning Hard Exploration Games by Watching YouTube. All right. Okay. So let's see details here. So I love this slide. Okay. So in Montezuma's Revenge, you get the first non-zero rewards, the reward when you get the first key. Now to get that first key, first you need to go down the ladder, you need to go down the rope, then down another ladder, jump over the skull, and going up the ladder 3. So you need to do all these things to get the first reward. And you know what was going to happen during the time on your model 3 PPO method? It's just going to be randomly exploring or exploring plus some exploration bonus. And that exploration bonus is going to be all over because it's going to be, oh, ladder, awesome, ladder. You get to learn the ladder, then you will not go to use that ladder anymore. Well, guess what? The ladder is just the first step. You have so many other steps. Okay, is that clear? So you need to get all these actions right to get your first reward. And if you sample actions uniformly at random, okay, so just the naive exploration, then you're going to get a reward about every 500,000 steps. Okay, that's the idea. Now, you're going to get that awesome reward. You spend 500,000 on average exploration steps, and you know what you're going to do? You're going to take that trajectory, chop it, throw it into exploration buffer with other 500,000 crap stuff, and that's it. That's all we're doing with Model 3. Model 3 is awesome, but it works when the reward is nearby. Okay, it works in fine-tuning your policy when you're already, the reward is nearby. Is that clear? So we need additional machinery that will allow us to, be able to execute, let's say, long horizon behavior, such as picking up the first key in Montezuma's Revenge. Is that clear? Do you understand the problem here with a naive model? Okay. So now, as the number of actions increase and as the horizontal reward increases, this probability decreases, the probability of getting the first reward. So now you know exactly why things are a little bit hopeless here with Model 3, with reinforcement learning, in the vanilla reinforcement learning. So let's try to put together the insights from that paper to see how we're going to fight this problem. The big insight is the following. I'll give you one demo, all right? And by the way, can somebody tell me why just imitating that demo, just doing behavioral cloning on that demo will not work, may not work to solve Montezuma's Revenge? Yes.
Like when you were saying when you raise one, the environment is
Right. So your colleague says, I gave you one demo when the pink master showed up at time 10:04. When the pink master may show up in a different time, you have no clue now what to do, right? Is this what you're saying? Exactly. So we want to be able to handle that stochasticity in the environment. Okay. So what are we going to do? So I think it's an interesting algorithm. I don't think this is very biologically plausible at all because resetting is not possible in real life. But we already know what to do. We already know that the biologically plausible way to do it is first you learn good representations and then you start moving in the world. I mean, babies take forever till they start moving. The first 2 years, they just look around. Okay, no, the first 1 year, they just look around, right? They move a little bit, but overall, they stay stationary. They cannot move on their own, all right? So 1 year, it's a long time. So here is what these people are going to be doing. I have the demo. I'm going to be resetting from a state from the demo. And guess what? I'm going to start by resetting very close to the end, okay? So once I reset, then I'm going to solve the task till the end of the demonstration. And guess what? This is an easy reinforcement learning problem because the horizon to reward is not large. Do you agree with this? Do you buy this argument a little bit? Okay. Yes. And when I start my policy, each time I reset myself, my policy uses the weights of the previous iteration. So let's say we have these time steps. First, I reset here. I learn to solve the task till the end. Then I reset here. My policy already knows from here to here. So I just work to get to that time step where from right on, after that, I know my policy will know and automatically will spit out the right actions. Okay. So when do you decide to reset? Well, you have a policy, you're learning this policy, you evaluate this policy. When you see that the policy gets on average rewards as much as the trajectory on that, then you're like, okay, now I need to move earlier in time. This reward can be external reward, but also time to completion. So it's able to get to the end, and also in a reasonable time. If it takes it too long, then you just keep doing reinforcement learning for that particular time step. Once you master that interval, then you reset earlier in time, and then you do again reinforcement learning to get till the end. Is that clear? Is this algorithm clear or? Yes.
Do you need to work your way backwards? Why can't you just work your way forwards and not reset at the very end? Can't you just say, oh, well, we reset from the beginning, then I just need to get to the next step from the one that was reset at the beginning?
Yes. Okay, sure. But this precisely, this assumes that you have an amazing state matching function. Okay. That, oh yeah, I realized that I reached that state from my demonstration, which these people don't invest on.
I see. Yeah.
Do you see? Well, they know, oh yeah, I solved the game. Do you see that? The external environment will give you that. Will give you the signal of termination.
I understand. Yeah.
Which is a little bit crazy if you think about it, because it's more natural. Me, I can figure out the states without playing at all a game. Okay, I can figure out the progress where I am. But this is a good question. But do you understand the answer?
Yeah. So they weren't just trying to get it to go to the to like the low dimensional pixel mapping or whatever. Like they weren't just trying to match it.
No, there's no matching here. There's no state matching whatsoever. It's like, oh, where I am in the demonstration trajectory time step. No, there's nothing like that. Okay. So you rely on the external reward to tell you, yes, you reached to the end. Now I say, okay, great. Let me start a bit earlier. And then you play, and you get, yes, you reached the end. You're like, okay, great. I'm doing well. Let me go, which is a bit crazy, but this is exactly what's happening. Okay. Is that clear? That there is no consciousness of where you are in the game. And the only thing you realize is, yes, I reached to the end. There is no explicit consciousness earlier on of how well you're tracking the demonstration's trajectory. Is that clear? Yeah. And they use, again, anything you want, PPO, A3C, any model-free method you want to use. I don't remember which one they decide to use, but it is irrelevant. That pseudocode is irrelevant to what model-free method you'll use. Okay, so let me show you visually. I love this picture. It really explains what happens. So first of all, I'm going to reset you right there, next to the key. The only thing you're going to learn is to get the key. It's very easy. It requires 2-3 actions. Then you'll explore, you'll get them. Okay? No curiosity exploration, just dumb random noise exploration. Once I see that you're succeeding in a reasonable time to get the key, then I'll tell you, okay, now I'm going to reset you earlier. Here. Oh, now you need to learn to go up the stairs. In the beginning, you're going to be falling off the stairs. At some point, you're going to manage to go up. And once you go up, your policy knows how to get the key. Because a policy is a matter from state to actions. So it still remembers the previous thing. So you rely on your policy, not forgetting, by the way, just to be clear. So you're able to do that. Then I'll reset you a bit earlier. And then earlier, now you'll be able to learn to jump the skull. And then you'll learn to go down that ladder. And then you'll learn to jump from here to here. And then I'm going to reset you in the beginning. And now I have a good way to get you to learn all the sequence of actions from one demonstration. Okay. Any questions here? Okay, well, that's fine. This is, by the way, just to be clear, most of the methods we'll see in this course is combination of imitation and reinforcement learning. This is also a combination of imitation and reinforcement learning. Okay, do you agree? Yes.
How do you know, like, what state is like state very right underneath the ladder? How do you reset to that?
Well, you have one imitation, one demonstration given to you.
Oh, right.
That demonstration is a sequence of states and actions. You know exactly those states. Okay.
Yeah, but you do reset to the deterministic state, then you're okay, right? So
Yes.
when you do that kind of stuff, you might reach like significantly different, different states that your policy might not have.
Well, you reset deterministically, but then you switch on the stochasticity of the environment. Oh, I mean, okay, in this particular thing, for example, there may be a monster killing you while you're jumping off the skull. You need to figure that out to handle it, let's say. But yes, during the descending, you reset deterministically, yes. Okay.
A few might have a hard time if it's like really stochastic and really weird things can happen, and the state can be far off from what you want the demonstration, and you might have a hard time.
Yeah. So the truth is that you can also use more demonstrations. For example, Go Explore used 4 demonstrations. Okay. And maybe so basically what they do, let me tell, they use different random seeds, and with different random seeds, you solve the game with the planning, the phase 1, the planner. And these different random seeds see different stochastic environments. And then you use all those to be resetting earlier and earlier and earlier. So different things, as you see, can maybe see dramatically different monsters and so on. Okay. A great question, though. Yeah. It's a great question. Yes.
Does it ever learn to take shortcuts? Like, for example, here the path goes off to the right and moves back around. If it was possible just to jump to the left, does it ever like learn to diverge from the demonstration policy in order to perform that?
Well, the policy itself is very highly either deterministic or a unimodal Gaussian. So it's not like now I'll decide to do that. It's not that multimodal in the first place, right? So it doesn't learn a lot of alternative ways to act in a particular state.
Do they later on do anything to optimize it, or are you just stuck following whatever policy you manage to find to get to that goal?
No, this is the optimization happens at every resetting. At every resetting, there is exploration guided reinforcement learning, standard reinforcement learning. So when I reset you here, okay, you're still going to be doing RL all the way to the end. So you're still going to be exploring here what's going on, but you're going to be in a very bulk. Your policy already will know roughly the right way. Still, there's going to be some exploration, okay? So you can be refining the way of going up the ladder. I mean, at some point, you're going to learn to go up the ladder really fast, okay? Because, yes, the later parts of the trajectory are constantly re-optimized, okay? But they're re-optimized while the weights of the policy are initialized in, whatever you learn from the first optimization steps, yes.
So as that optimization goes on, will it ever learn, for example, at the bottom of that top ladder, jump to the left in order to save all that time going on the stall?
I mean, if something, yeah, sure. So an action can totally suggest going this other way, right? But probably you cannot get reward because probably you fall. So now, if assuming you could, yes, so you could, yes, because you are exploring. All right. Now, this would assume that the trajectory is very short in the first place. So the only thing you need to get the reward means that jump to the left, get the key. Okay. So yes, sure. Assuming that your model free RL optimization can discover those actions in a reasonable way. So that, as we saw earlier, right, the more the actions and the further the reward, the lower the ability of such discovery to emerge. But yes, in principle, yes, it can learn that.
But if you had a shortcut that was, go through one room instead of 7 rooms, that would still be a long horizon, which would limit the ability for the model 3 to find that, correct?
Yes, it wouldn't be able to do it. But if you discover something awesome here that the trajectory didn't show you, I think you can keep using it. I'm just going to see that, oh, yeah, you succeeded much earlier. Let me reset you earlier. I'm not going to, stress you out to follow the later steps. Do you see? Yeah. Okay, so let's continue here. Oh, playing by watching YouTube. We need to cover this next time. But we have seen some of the count-based exploration. Yeah, we saw that thing with the hash tables and so on. Yeah, so they do much better. Now, let me show you what these people did. These people, we go back now to go explore. We close the parenthesis of learning from a single demonstration. And so Go Explore was able to score that high here, okay? And all previous methods were around there. So DQN is down there, A3C, Impala is some DQN++, I think. Oh, no, Rainbow is DQN++. Impala, I think it's A3C++. I'm not actually sure. Dual, yeah. Well, that's it. So as you see, huge improvement. Okay, and there's no humans experts here. It's just the algorithm first plans in a deterministic environment and then it imitates its own trajectory. Now, this did start a discussion in the community about, are you allowed to switch off stochasticity in the environment and so on? I think it's a bit crazy. I mean, sure, you can try, and this is not what you should get stuck on. I think what we should get stuck on is, of course, if we had awesome representation, we'll be able to figure out where we are. We may not even need to, worry about switching off the stochasticity because we will know each time we see an observation where we are in that state connectivity map. Okay. Now, the problem is that right now we don't have good representations to tell us, that state information, where we are in the things that we've done before. Do you see what I'm saying? Recognizing the situation. So situation recognition is not there. And here is why. Then at some point, so this is where Go Explore were. And look what happens. This is what Go Explore did. And here's what happens. If you add that information, you tell to the state what is the room number. You tell to the state if you have a key or not. You do so much better than all previous approaches simply by informing that algorithm in which room you are and how many keys you have, which is very basic visual detectors, very basic, maybe type 2D slam type to remember, how much progress you made in the room and so on. Let me show you here. Yes. Well, yes. So this is the domain knowledge. The domain knowledge is about room number and whether you have a key. Yes. Questions here? Yes.
Is there any way that you can do this with a more sophisticated representation of the state space, like the matching, and maybe you can learn about whether or not you key itself?
Yeah, this is a great question. So the answer is I do not know. There hasn't been such a method so far. Does this make sense? Why there may be some limitation there? Because when you see a state, you saw them on the zoom-up picture, right? There was a cave, there was a stairs, there was a key, there was a little boy, and so on. So a state has a lot of different components. You want to keep track of those components, okay? What is the room number? Do I have the key? Do I wear a hat? Did I kill the monster? So the representation is a set of individual pieces of information. Right now, the state embeddings we have are super unstructured and learn from the whole picture as well. Is that clear? Also, you see a key, then maybe the key goes out of the picture, you forgot you got the key. That's the other nuts thing, that you don't have a ways to have a history of itemized information of what has happened. Does this make sense? So we don't, right now, and this is all things that the symbolic AI would advocate. Oh, we need symbols, we need symbolic representations. Well, it turns out these symbols are hard to mine from pixels. You know, you say, oh yes, I want to have a key, and then you don't have a good key detector, for example. These people did not use, they decided to give that unique information, but they didn't give it through Oracle. They built key detectors, and they built some method to keep track of a room number, okay? It's just they engineer it inside, all right? And they were able to do so well. So I would say, yes, I think there's going to be amazing progress the next 1 2 years on such, let's say, modular state representations that keep track of the information in that decomposed way.
That's going to be symbolic, you think?
And not symbolic, but just little feature vectors, but for the different things like key and so on and so forth. You figure out that the different entities, etc., right? Does this make sense? Mm-hmm. Symbolic in the sense the key can still be remembered as a feature vector, right? Much like our detectors, when they detect keys, you know, what is before the softmax is a long vector, let's say, okay? All right, because it may not be the key, maybe the key is damaged, or the key has 3, extensions, or the key is the pink key or is a gold key. Do you see what I'm saying?
Yeah.
There may be a lot of things that you want to keep around,
mm-hmm.
Okay? Yeah.
Is there a way of doing that without changing like
Yeah. So I think a very good paper to read is from Berkeley and Alyosha efforts. They talked about priors that humans bring when they play video games. So the priors we bring is about, oh, keys are good, keys go to doors, tunnels are great, tunnels are to be traversed. So we are very, very diverse because we have experience with the real world for many, many, many years, and the real world can be diverse. Or with a lot of video games, but with diverse virtual worlds. So we bring this knowledge in when we play a new game, okay? So ideally, our artificial agents also need to build this knowledge in. The knowledge about how the world works, what are the important entities and how they are, and their affordances, how to use them. So this is precisely the big open question in AI, how to endow agents with this type of knowledge and in a form that can generalize from environment to environment. So you just have one agent whose knowledge becomes larger and larger and larger and can be used across diverse environments, which means your key representation better match and detect this other fancier key or weird looking key, right? Does this make sense? Good question. Other questions? Okay. Well, we covered the paper. It took us some time. Yeah, so now here is the other crazy thing. The phase 1 takes 1 hour. And phase 2 takes 1 day on 16 GPUs. Okay? Because why it takes so long? Well, because we use vanilla model-free reinforcement learning. I mean, if model-free reinforcement learning had improved, then we would be doing better on the second phase as well. But this is interesting just to know, okay? Yes, this is similar to graph search plus robustification. The graph searches are good for learning the model of the environment. And this is the end of our intelligent exploration lecture. And please let me know if you have any questions, because now I'm going to switch on to the next topic for today, okay? Okay.
So in an earlier slide, I think where you showed phase 1, phase 2, you said phase 2 if necessary.
Yeah, if the environment is not deterministic.
Oh, so if you're doing that, they should see like how phase 2
Yeah, super important. For Montezuma reverence, it's impossible to do anything because you cannot learn anything. Like even if the master comes half a second later, you are going to mess up. Okay? Other questions? Okay. Well, you don't need to worry. We have enough lectures to cover everything we need to cover. So don't worry if we don't finish today's lecture. We'll continue on Wednesday. Okay? some very interesting, again, very exciting. Now what we're going to discuss, very exciting, which is the following. There is a big discussion in the community about the value of learning by interaction. How important it is to learn by interaction. Also, what interaction means. For some people, interaction is really to be able to use your hands. By interaction can also mean to move your camera around. And the question out there is, how much can I learn by observing others, okay, or me observing the world? I mean, I should be able to move around, okay? There is an interesting kitten experiment where one kitten was able to move around and choose the way they would move their head. The other kitten was not able. He was moved around. The other kitten was driving it, but he was not able to choose where to go. And the kitten that both was choosing actions of where to go, was able to see, was learned to see. And the other kitten was just driven around. He didn't learn to see. So choosing your own actions to know also, how you moved your camera turns out to be important. Let's assume that we can move around, that we can have agents that move around, or even if we give them passive data, we can compute the camera pose. We can compute how much a camera moved, okay? This is the information that you have for free if you yourself move the camera. You have the estimation of your head pose, okay? So in any case, the question is, how much can we learn by observing? If we can learn a lot about the world by observing, then this is great because we don't need a lot of interaction data, okay? Is that clear? Okay, so we call this learning by observation. Now there is a particular subfield of that learning by observation, which is called offline reinforcement learning. What does offline reinforcement learning means? It means that it's not learning by observation. You still have access to the states. Okay, there is a big representation learning problem here. Learning by observation means I'm just watching and I have computer vision to figure out what's going on in the world. Offline RL means I have access to state action rewards. It's just I didn't collect those state action rewards. Is that clear? These are huge different assumptions, but in both cases, I will not be acting in the world. I will just consume the data of the other person. Now, this is very similar to kinesthetic imitation versus visual imitation. Learning by observation is just visual imitation. We're going to have one more lecture on that. Offline RL is not visual imitation. It has access to the state information. So this is what we're going to start today's lecture with, offline reinforcement learning. If I don't get to collect my trajectories, can I learn an equally good policy? All right. And we'll start from a paper that I found exceptional. Okay, exceptional paper. We'll give you some insights. Of what works and what doesn't work, and how model-free methods rely very much on the assumption of being on policy, or quite a bit on policy. Okay. So what does on policy RL means? It means that we have a policy, and we improve that policy using data collected by the same policy. Okay, or by slightly more, obsolete versions of that policy from earlier iterations. But so what we call so far off policy, we said DQN is off policy. The different policy that collecting the transitions was the same policy, but with earlier weights from earlier training iterations. Is that clear? We call those methods of policy. This is not really off policy. This is not really a different policy, just the same, but from earlier iterations. And the truth is the following. If you use really off policy DQN, it's not going to work. Okay, and now we're going to understand why. So basically, those different policies were still super correlated to the present one. Okay, so that's why I didn't want to put a lot of emphasis on and off policy, because it is not a binary concept. That was very slightly off policy. Now we're going to see really off policy RL. And instead of calling it really off policy RL, we also call it batch reinforcement learning. Like I give you a batch, which means I give you an experience buffer ready with trajectories on. You need to learn something from it. Okay. Not that much of policy after all. So batch RL is we consider the following setup. So let's all focus now to understand the setup. I'll give you a fixed experience buffer, which you did not collect, okay? And it will not grow with data and you should be able to learn a policy out of it. So who can give this experience buffer? Anybody. Some experts. It can be some other algorithms, some other learned policies, and so on. Is that clear? Now, is this batch RL clear as a setup? Okay, so if it's so clear, I want to ask you, how is this different than kinesthetic imitation learning? Yes?
You're not necessarily trying to repeat what you see, you're just trying to learn that to develop your own policy.
You don't want to imitate what you see, okay? But not necessarily, but want to develop your own policy because you have access to the rewards as well, okay? So, and the hope is what? The hope is to learn a policy that is even better than the guy that collected the data, right? Let me give you a realistic setup. Imagine and actually you're going to see this paper at the end of today's lecture or next lecture. You have demonstrations. You ask people on the internet, teleoperate this robot to do all these pick and place tasks, and the people do this thing. Oh, I dropped it. Oh, okay, here I put it there, and so on. And they give you chopped trajectories. Okay, all the time they make mistakes because they haven't teleoperated the robot. You need to take that messy data and learn a policy that is better. Okay. Is that clear? That doesn't have the same mistakes. The policy you're going to learn should not be dropping the object in the middle. Okay? Is that clear, the set? Okay. Okay. So I don't give the driving example because for driving, it's just extremely difficult to supply rewards of good driving behavior. Okay, that's the problem. So there you say, oh, look, I have all this driving data. Now I'll assign rewards. I'll learn to drive better than all the other drivers. Well, assigning those rewards is very, very complicated. Do you see what I mean? Because to avoid an accident, you really may need to jump on the sidewalk and so on and so forth, etc. Okay, so off-policy reinforcement learning. So off-policy RL methods are methods that improve a policy using data collected by either another policy or another expert. And here you have a side-by-side on-policy RL and off-policy RL. In on-policy, you have the data, you take the callouts, you update the policy, and you deploy that policy and collect additional data, okay? For batch reinforcement learning or truly offline reinforcement learning, you cannot deploy that policy. Do you see? So you just learn a policy, and then you go and test it. Do you see? You don't get the opportunity to collect more data as you train your policy. Is that 100% understood? Okay, let's move on then. Well, what do you think? What if we just apply standard off-policy RL methods in this setup? The way off-policy was presented earlier in the course is like, oh yeah, I have one policy collecting data, I have another policy that I learn, and so on. What if I take your experience buffer and I train DQN? What do you think about this as a baseline? Or DQN I would train if I have discrete actions. The other off-policy method, if I have continuous actions, is DDPG, deep deterministic policy gradients. Oh, okay, this is the continuous analog. So this is exactly the first experiments we're going to do, okay? And the paper that you need to read for today's lecture is off-policy DeepRL without exploration. We're going to have two DDPG agents. We're going to have the DDPG behavioral, the orange one, which is going to be the one collecting the data. And we're going to have the blue DDPG, which is going to be learning from that data that the orange one collected, okay? And we'll consider three types of data, okay? The first is going to be a final buffer. As you're training your DDPG agent, at the end, once it learned, you'll go and collect. So we'll train DDPG for 1 million time steps. We'll have a little bit Gaussian exploration noise. We'll store all the experience transitions. And then we'll take this experience buffer and give it to the blue DDPG to learn from. Is that clear? All right. So the imitation buffer, let's go to the third one, is that first we're going to train a DDPG agent. We'll see that it trains great and is doing very well. And then we'll consider it as an expert. We'll deploy it in the environment and we'll collect 1 million transitions, populate the buffer, and give it to the blue DDPG agent to learn from. All right? And the concurrent one is we're going to train the two agents concurrently. They're going to start from scratch, random weights. One is going to be deployed in the environment to choose its own actions, and the other is not. Okay? That's it. By the way, notice that 0.5 is higher exploration, high variance in the exploration noise than usual, just because I want to have more diverse transitions on that final buffer. So each transition experienced by the behavior policy is stored in the buffer replay where both agents learn from. So both agents are trained with the identical data set. However, I'm not going to tell you how they differ, so you'll figure this out on your own. But do you understand these three experience buffers? Do you want to ask some questions here? I think the last one is super clear. I first train a RL method and just use the trained method to collect transitions and make a buffer. The middle one, the concurrent, is also very interesting. We have the two methods. I just trained the DPG, and as the data are collected, both blue and orange sample from it. Okay, it's just when you deploy in the environment, the agent we query the orange, not the blue one. Okay, of the argmax, right? And you deploy in the environment the action. And the first one is just you train a DPG from the beginning till the end with a lot of exploration noise to make it diverse. You have insane amount of transitions, and then you give it to the blue agent to learn from. Okay. Now, do you have questions? Because the question for you now is, what do you think it will happen to the blue agent? That's the question. What do you think will happen to the blue agent in the three cases? Let's start from this guy. But by the way, we are not going to do behavior cloning, okay? We're not going to do behavior cloning. We'll use this batch the same way we sample from experienced samples during training of DDPG, okay? Is that clear? Okay. We'll be learning a Q function, if you remember how the DDPG works, and then the way it updates the actor is backpropagating through the Q, okay? Okay. Do you have an idea here what's going to happen? Yes.
It may not work.
If
it does work, it may have a more brittle policy.
Yes, and why?
Because it's not getting a lot of examples of what not to do, or we can't understand sort of what's happening throughout the environment. It only sees very limited, that's supposedly good. It doesn't know how to get back on track.
Right, but here in the concurrent buffer, the orange guy also sees identical things. So why the orange guy does so much better than the blue? Yes?
Because the things that it sees are the states that it tends to end up in. So if the blue buffer is, let's say, driving the car, it's always driving off. The orange buffer is driving off to the left. That's the one that we're learn, okay, here's how we recover from that specific error. But the blue buffer, if it's constantly driving off to the right, it doesn't get that feedback of how to fix that specific issue.
Excellent. Let me try to restate what your colleague said. How does an RL agent choose actions during training? This is what we need to understand. Well, it chooses the actions that it thinks have high Q value. Okay, do you agree? That's we do argmax essentially. That's how we deploy a policy. Means you take the argmax, noisy argmax, you add a little bit of noise, and you deploy. So basically, when you learn a policy, you get a policy, you have a Q function. This Q function thinks that for particular states, these actions are good. Then you deploy those actions in the environment, then you get slapped. You're like, oh, okay, I thought it was good, but turns out it's not. Okay, so now your colleague says is that this blue agent may be thinking that going to the left is a good idea, but it doesn't have the opportunity to actually deploy it in the environment to get a slap. Do you see? And now a good question would be why the Q functions of the two agents are not identical since they experience exactly the same examples? Well, there are two neural networks. They may have different initialization weights. Okay. So the same examples, different weights initializations result on different Q functions. So RL critically depends on the fact that when you think that something has high Q, some state and action has high Q, that you deploy it in the environment and the environment corrects you. Does make sense? And the blue agent doesn't have this opportunity. So this is exactly the problem. Is that problem understood? Now we'll repeat this analysis here. Yeah. So this is the concurrent buffer, and it's actually doing also pretty pathetic. I thought it was very, very interesting example. So here, these are the orange and the blue trained on 3 different RL environments. So these are slides from this paper. So the orange agent and the blue agent are trained with the same of policy algorithm and on the same data set. Consider the concurrent buffer. And the difference is that the orange agents use the standard RL loop. You collect the data, store them in the buffer, train, repeat. This agent guide never interacts with the environment. It just uses the trained data collected by the orange agent. One interacts with the environment, the other doesn't. And of policy deep RL fails when it's tested truly of policy. This is what you need to remember. It doesn't work for the reason that we just said. Okay, what is the reason? The Q value estimates, check the Q estimates here, guys. I think, yes, look at the estimated values. The estimated values of the blue guy are much, much higher than the orange. Blue thinks the world is a beautiful place. It has Q high everywhere, and it doesn't get the opportunity to experience the world to see that this is not the case. Okay. Yeah, so this is exactly it's called extrapolation error. The Q function trained from a fixed experience buffer has no way to know whether the actions not contained in the buffer are better or worse. Okay, that's the thing. So the actions that don't show up in the buffer may as well have much higher Q values, and you don't have a clue about that. Okay. Okay, so here's the extrapolation error. This is precisely what happens during an update for the Q function. Okay, this A prime is just generated, and you sample here from your data set. Here you deploy a policy. The alpha prime is the argmax of that. Do you see? So your data set is one thing. What the argmax is going to do is a different action. May as well that action doesn't need to be in your data. You're taking an argmax. Does this make sense? The argmax is not restricted in any way. The result of the argmax to stay on experienced actions. Is that clear? This is very important to understand because that's the fix in that paper. Let me tell you the fix in that paper. It's very simple. You learn a generative model of actions. Okay, how do you learn it? Well, conditional VAE. So it's just essentially a policy. Conditions on you train it as a CVAE in the sense that it's a multimodal policy because it is take a stochastic variables as input, much like the CVAs we saw in the previous lecture. So you train a CVA for your policy, the way that we'll see again, and then you sample from your CVAE when you do the argmax. Okay, so you don't do argmax across all possible actions. You only optimize across the actions that you've seen from your buffer. That's it. This is the fix. Precisely exactly the problem. Is that clear? Yes?
Could another solution be like the initialization to be really sort of pessimistic value estimates?
But how? You cannot control that. That's the problem. Because it's a neural network. It's not like we have a table of Q values like, oh, let's set them all to -100. Do you see? There's not a table here. It's a neural network. You change the weights and the Qs of all states and actions change. Okay? All right. So here is precisely the problem. For S primes and A primes not part of the data set, the resulting Q estimate is bad. And because this is bad, when you're updating, you use it as a target for your Q. This is also bad. Do you see the problem? And then you mess up your Q function in a way that you cannot recover. That's it. Is that clear, guys? So basically the orange, so you take the argmax and you query your Q for that A prime, and that is a noisy estimate that because you use that as a target, then it contaminates your Q values from now on. All right, I think we got it. Okay. So what is the solution? The solution is as follows. Instead of the standard way of updating your Q, you're going to do argmax, not across all possible actions, but only across the S prime and A prime that are, a part of your replay buffer. All right, is that clear? You're just going to not only take argmax across all possible actions, you'll take the derivative across all the range of all action coordinates, but only across the generative model of your actions. And now you're going to see how we're going to do that. So this is called batch constrained Q learning. So we're going to do Q learning, but we'll constrain the actions within the batch. We'll train a generative model, okay, to provide action samples that match the action samples in the batch. So here is our generative model, is our policy essentially. Just given a state is going to give us different diverse actions. So that policy is not going to be a Gaussian anymore, okay, because we need some diversity, all right? And so we're just not going to model the action directly. We're going to model this additional. A is going to be, let's say, the average plus the additional residual. And we're going to consider, this type of generative model, as we said, during the argmax. That's all. So how we're going to do that? Well, you remember how we trained before conditional VAEs? We're going to train a policy that will take as input not just the state, but also some random vector. Okay? Simply because, and we said last time that this will, as the random vector traverses the Gaussian, the multivariate Gaussian of 0, mean, and unit variance, the output space will traverse the manifold we care about. That's what variational encoders do, right? You put down that architecture, you train it with variational encoders, or in our case, conditional variational encoders, because the red is the conditioning information, and the result is a model that has the input latent, the input random noise here, the Z, traverses this constant multivariate Gaussian distribution of 0, mean vector, and identity covariance matrix. The output actions traverse the manifold you care about. And what is that manifold? The corresponding actions in your batch, in that experience fixed buffer. Is that clear? Okay, so just a quick refresh. It's going to be pretty quick because last time we did exactly the same. We see the Z in the input is always sampled from the constant multivariate Gaussian distribution. Let's not maybe repeat all those. Well, I put them here for you, just in case you want to look at them again. Let's jump directly to the conditional variational encoders, which is exactly this. Our conditioning information is the state, okay? And what we care to predict is the actions. That's it. So I'll give you the data set of state and actions, and you'll train your model exactly this way we discussed last time, okay? Minimizing the KL between the prior and the variational posterior and maximizing the reconstruction error. Is that a little bit clear? Like now that you know that you can go read the paper and come back with your questions if you have a question. This is a standard CVAE for the actions. By the way, you need to learn that. The next paper, IRIS, which is very interesting, it's a very large scale teleoperation collected data. It uses identical method, guys. It uses identical method. Not only that, but it also uses another CVAE for a sub-goal prediction. So I do believe that spend some time to read this amazing Carl Dorsch tutorial on CVAEs. Have you read that Carl Dorsch tutorial that we linked on the website? Okay, so it really is amazing. You really need to read it, okay? It is very well explained, and you're gonna love it, and it's gonna show up again later, okay? Okay, and we'll make sure we add some questions on CVAEs in quiz 3. So please read Carl's tutorial, all right? So batch constraint Q learning, I mean, okay, it's 110, but basically what it does is very much like DDPG, okay, or DQN. And the only difference is here, where essentially they sample a bunch of actions and they perturb them, and then they pick the argmax. So basically there's an explicit sampling from a policy that only predicts actions that has been seen in the batch, okay, as opposed to having the derivative through the Q function, if you remember. All right, there is some complication here with the perturbation, but it is not such a big deal, okay? It's not such a big deal. Yeah, I don't think it's such a big deal. But we'll be back. So on Wednesday, please join the Zoom. We're going to send a Piazza message with the Zoom information on. We'll complete this and we'll move on to much more interesting learning by observation method, as well as sim to real, if we manage to start that topic. Yes.
Is that the Zoom that's the makeup from last Wednesday, or is it separate?
No, that's it. It's a makeup for last Wednesday. Okay. Yes. So it's going to take place this Wednesday in the scheduled time for lecture. Okay, great. See you there.